Hey there, this is Jeff. I'm covering something a lot more serious than board games and video games. Um, some of my titles don't make any sense, so ignore that. But I just created a procedure that can predict any prime number in the world, including unknown primes. And I know that sounds unbelievable. Uh, Bear with me. I have my work here for everybody to see, and of course it should get some scrutiny and people should try this on their own and all that jazz. So, anyways, let me open my document and show you what we got. That is not the one I wanted to open. Hold on a second. Okay, so I found that prime numbers follow a repeatable frequency. And I know that sounds amazing and impossible, but it's true. So what you have to do is you have to form a prime Hankel matrix, which I know sounds crazy. And here is the math. I'm going to zoom in so everybody can see the formula. Basically, what it is it's a linear algebra style matrix. So think of it as so if I have a matrix that says 1, 2, 3, 4, right? And then I have a mirror of that matrix. This is a very small matrix, mind you. So now I'm going to take these two numbers and multiply them together. So I got 1, 2, 3, and 4 again, right? And then this should also be 2, 3, and 4. It's a mirrored matrix. And here you're going to get 4, because that's 2 times 2, right? 3 times 2 is 6, 4 times 2 is 8. And then this is 2 times 3 is 6, 8. And then here's 3 times 3 is 9. And 3 times 4 is 12. And then 4 times 3 is 12. And then 4 times 4 is 16. Right? So when you do something like this, you get, this is called the diagonal of the matrix right here. So what I'm doing is I'm creating a matrix, any matrix. And if you do it using prime numbers only. So instead of 1, 2, 3, 4, prime numbers start at the number 2, by the way. Number 1 is not a prime number. So it would be 2, 3, 5, 7, and then I think it goes up to 11, right? So it's going to look like this. 2, 3, 5, 7, 11. And I don't want to go through the whole thing again, but what we're going to do now is we're going to multiply these together, and the answer is normally 4. But these are prime indices, or I call it the prime domain. So the number 4 doesn't exist in this domain. You have to use the next closest prime number. So that's going to be 5, is going to go there. So 2 times 2 is 4. That's not a prime number. The next closest prime number after 4 is 5. And so if we come here, and I'm only going to focus on the diagonal, because the diagonal is all that matters. So 3 times 3 is 9, so this one's going to be 11. 5 times 5 is 25, and I'm really horrible at figuring out primes in my head. I think 29 would be the next one. And then 49, oh gosh, 53? I might be wrong on that one. And I'm not even going to bother doing 11 times 11. So, so anyways, you can see that it forms this diagonal here when you do this. And you can fill in the rest. I mean, there's nothing wrong with it. It's just that the rest doesn't matter. Like this is, whatever number that would be. This would be 7. And so forth. It's going to be a mirrored matrix, just like you see here. where the numbers below the diagonal are the same as the numbers above the diagonal. That's the key thing. That's a Henkel matrix. And so the Henkel matrix, the diagonal of that matrix, the thing that I just showed you, forms a harmonic structure. It literally has a frequency that repeats. And it repeats throughout all known numbers. It doesn't change ever. And so this is the definition of that frequency. And there's a discrete Fourier transform, which all I'm trying to say is that so if D is the main diagonal of the prime Henkel matrix, the Fourier transform has dominant frequencies. And then the inverse, so let me back up. So these frequencies are dominant, and they're repeated, they're predictable, they're unchanging. So what this means is, using the frequencies alone, I can reverse transform them and create any prime diagonal in the known universe. All I have to do is just use the frequency, and you could create any diagonal in the known universe. Now remember, that diagonal is a multiplication of two primes, so we're not done yet. Then you have to figure out which two primes equal that diagonal, and that's how you can find unknown primes. Because, and I'll get into it, I have a formula for that as well. So given a predicted diagonal, the index can be interpolated to figure out what the next prime is. So when you're using the frequency domain to predict a diagonal, there is a scaling formula that must be used, because the magnitude of the frequency changes as you increase in the number system. So if you're looking at really low numbers like 3, 5, 7, 11, those lower numbers are going to have a much smaller magnitude. And then as you approach infinity, the magnitude is going to also approach infinity. I'm sure, I'm not a mathematician, so I didn't do like upper bounds or anything. But as the numbers get larger, the magnitude gets larger. So you have to use this formula to scale it. If you don't scale the magnitude, then your predicted diagonal will be wrong. So here's your empirical procedure. So what I did was I generated prime numbers that are known in the universe. I created a 1000 by 1000 matrix using the sum method. I didn't use the frequency. I extracted the main diagonal and identified the 7 dominant frequencies. That's what this is, right here. And then I reconstructed the diagonal by only using the frequencies, and basically compared the two to make sure that my predicted Henkel matched the Henkel that I constructed the traditional way. And ignore this part. Here's the next observation. So you have to scale your magnitude. You also have to deal with phase drift. So it's a cosine function. Right here, it's a cosine function, and so the phase shifts. As you go through the number system, the signals remain the same, but the phase shifts. And so I identified all the phase shifts, and you have to apply this formula to shift the phase depending on where you are in the number system. And all that's laid out here. So the dominant harmonic components are clean and linear, but you have to deal with phase shifting. And then right here are the 7 frequencies. Now the magnitude you see here was the empirical 1000 by 1000 matrix. I picked a matrix that started at the number 5000. So we just picked something at 5000, and then we made a 1000 by 1000 matrix from there. And anyways, I had a list of known primes up to 5 million, so I could do this experiment. But anyways, these are the 7 frequencies. The magnitude is just what we measured empirically, and then of course this formula um, that I provided is is based off of these magnitudes that I listed here and observed. And then the phase drift, I just explain it again. I repeat a lot because this document is a living document from me learning things as I go. I keep adding notes so I don't forget them. And then it says conclusion and future work, but I would like to show. So this is a Python script that I wrote that so we created a Henkel matrix with a sum of primes. We applied phase adjustment and diagonal, scaled the formula, and we accounted for the drift, and we created a diagonal, and then when I say we, it's just me, I was able to reverse engineer that diagonal to the 2 primes that are used to make up that diagonal. Since it's a symmetrical matrix, there's properties that allow you to do that. And anyways, let me get to here. So this right here, or actually what I meant to do was open the file. But anyways, this right here is the actual Henkel matrix if you use the sum method. And then what you see superimposed on top of it is my predicted using only the frequencies. Those 7 frequencies plus the proper phase adjustment. And you have to scale the magnitude of those frequencies, right? So using only those frequencies, scaling them, and phase adjusting them, I created a Henkel matrix. And then I created it the old-fashioned way, using known prime numbers that we know about in the universe. And I was able to create a 100 by 100 Henkel matrix that perfectly matched. It's 100%. So, what does this mean? Well, if you know these Henkel numbers, you can then reverse engineer them to get back to the prime. And I think I have that here for predicting prime. And some of this is going to be a repeat because I tried to repeat myself a lot so I wouldn't forget. So remember, you have to scale the frequency. This is again a procedure just trying to help people to understand what's going on. And then here's the formula for factoring. So here's your algorithm. So if you have a diagonal, you can check for prime pairs to see if that's a prime number and return a prime pair. This might need a little bit of work because what we did here is we were testing it, right? So I think that now that I'm looking at this, I think I'm using prime numbers to figure out what the prime numbers are that equal it, and that's bad logic. So if you're trying to find an unknown prime number in the universe, this is my struggle, and this is where if there's a mathematician out there that can help me, I'm not a mathematician. I would love the help. So if we create a Henkel diagonal that's at some really large number, right, where beyond where the current known highest prime number is, there's got to be a way that you can derive the two numbers that were used to make that number. And or at minimum, it narrows down for you how to find the next largest prime number, because you know that there's two prime numbers that are going to equal that, and there's a real high chance that that one of those two prime numbers is a new one. And so, I know they have like all this software out there where they take all these different numbers and are trying to see if that's going to be the next prime. What I'm getting at is this can narrow that scope immensely, because if you can just predict these diagonals, you may still have to do some crunching of some kind, and that's where the math is starting to get beyond my knowledge. And some of these formulas, and the reason why I was admitting that this algorithm isn't going to work, sometimes I'm like having tools like ChatGPT help me to derive what these formulas are. Like I'm like, oh, this is my observed data. Can you help me fit a function, right? And so what it did here is it helped me fit a function, and it worked, mind you. It completely predicted the prime numbers properly, but my test failed because I didn't look into the algorithm that it gave me. It's using prime numbers to predict prime numbers, and that's stupid. What I was trying to do was construct a test where it predicted, like we figured out the prime numbers from the diagonal, as it, pretending like those prime numbers were never known to the human race. But of course, I'm using prime numbers that everybody knows about. That's the whole part of testing, right? Is you take a known outcome, and then you predict it as if you didn't know what that outcome was. Anyways, what ChatGPT did here is it gave me an algorithm that uses prime numbers to find itself, and that's not going to work. Anyways, so again, here's the 7 frequencies. Here's another note about the phase drift, and of course it says I do have my script, which created the Henkel diagram. So, and you can see like this is the average drift. Has to be calculated in based on the size of the matrix that you're creating, and it also depends on where in the number system that it's happening. And I have several documents here that are very similar with each other, but anyways, this is I think the one I was looking for, but anyways, that's what I wanted to show you today. So I wanted to log on July 3rd, 2025. I think the biggest breakthrough is I found a frequency in the prime number system. A frequency that's completely repeatable. And I firmly believe it can be used to predict the next prime. That's the part where it's beyond my current knowledge. And I have my information, and I'm more than happy to share it. Obviously you can see my notes are scattered, largely because I just I'm trying to do something pretty major here. So, anyways, this is something that I just wanted to share and use this video as an opportunity to share those findings. Now, with that said, there's also and I thought it was a Toeplitz matrix, but it's a Henkel matrix. So sometimes you'll see certain names and you'll say, hey, that says Toeplitz. It's a Henkel. This is just because I'm not a mathematician and I sometimes don't know what I'm talking about, but I trust me, I do know what I'm talking about. This frequency thing is real. And so you can see I have a frequency domain, and I discovered this while I was trying to look at the Goldbach conjecture. And so for the Goldbach conjecture, we have a frequency domain here. So I have a discovery on this one as well. And it's doing something similar. So let me go back to Excel here. So let's say you have the number 3 plus 5. Normally that's 8. in the regular number system. But actually, let me back up because ChatGPT taught me to think of it differently. This is how I figured it out, but it taught me to do it differently. So Goldbach conjecture is that every even number to infinity has two primes that add up to it. So, for example, 1 plus 3, well, I'm sorry, 2 plus 2 is 4. Those are two primes. 5 plus 7 is 12. That kind of stuff. So, to understand what I'm going to get into next, we're going to, use some terms here. N equals even numbers for Goldbach. So this would be 2 to infinity. Okay, the infinity part, you're going to have to bear with me because mathematicians have a very strict bounding proofing that they require, and I did not proof it to infinity yet. I'm trying to figure out how do I do that, and you'll see that when I get into this. But what I want to share, though, is I found a frequency for Goldbach, and it's very similar to the frequency for the prime numbers for the Henkel. The Henkel one's actually more complicated. This one's simpler. So n is the even numbers for infinity. So then what we do is we have what's called n minus and n plus primes. So what that means is it's the prime numbers immediately or closest above and below the Goldbach number n. So, for example, if you're looking at the number 6, then it would be surrounded by 5 and 7. Or let's do it maybe a cleaner way. So if this is n, then you would have P1 is 5, P2 is 7, and delta is 2. Delta is just 7 minus 5. That's all delta is. All right. So let's take another one. Let's take 12. Then you would have 7 and 13, and then 13 minus 7 has a delta of 6. Okay, and so forth. Right? Are you getting the gist of the delta? Okay, so the formula here is n mod delta. So mod is just a term for you divide the numbers and you look at the remainder. So if n is 12, well, let's do the same one. So we had 6 and we had 12, right? So n mod delta, 6 mod 2 is 0 because 2 evenly divides into 6. And then this one is also 0. And by the way, 0 happens a lot. So let's see if we can find one that doesn't have 0, because they do exist. So if it's 14, that would be 13 and 17. And so that would get us 4. Here we go. So with 14 mod 4 is, 4 times 3 is 12. That would give you a 2. So as you, and then you would have to fill this in, right? So it should be 2, 4, 6, 8, 10, 12, 14. Every one of these has an n mod delta, right? So we figured out like this one's a 0, this one's a 0, and that one's a 2, right? And so as you fill in these numbers right here form a frequency. A very repeatable frequency. Now, like I said, I'm trying to show that it goes all the way to infinity that way, and that requires a much more rigorous mathematical proof. And that's the part where I could sure use the help of a mathematician. I'm trying, but let's now jump to the document. So I'm going to zoom in here. So here it's just explaining for each even number, p right and p left is the prime that's above and below it. The count of Goldbach pairs where n was grouped by delta, revealing distinct modular clusters. So we did a Fourier transform on it again, and that's all that is it, because it forms a frequency, we're doing Fourier to figure out where the frequencies are. So we're doing a mapping of the frequency. So there's some. So for every even number, it can be uniquely assigned to a delta, which is a prime number domain, defined as the smallest prime gap. So all it's saying is if you take the prime number that's less than the even number, that's less than the next prime number, you have this delta, right? For every even integer, there exists these primes. This stuff repeats itself a lot. And then you can see that it forms and satisfies this equation. Okay. There is a modular periodicity of these counts. So let's get into, so here's there's a frequency that has a discrete Fourier transform. Discrete because we're looking at only integers. We're not looking at whole numbers. So that's why we have to use the discrete transform. And this is attempting to bound it. This is not enough. This is a theorem. I don't have the proof for the theorem on this, but this is my theorem, is that it, as you go to infinity, is bounded. There's an upper bound and a lower bound. We can create a harmonic reconstruction, and here's the formula for it. And ChatGPT helped me to create this. I have to use tools. When you're talking Fourier transforms and analysis, I have to use tools. I'm not smart enough to do this stuff by hand. But anyways, this is the formula. And here's the thing. The raw dominant harmonic amplitudes of Goldbach's prime count sequences are excessively large. So every time we tried to bind it to the lower bound, so basically I was trying to go to infinity and capture the lower bound to prove that these frequencies go all the way out to infinity and never, changes behavior. The amplitude of these harmonic frequencies, basically it goes to infinity too early. So it gets too large, and what it does is it causes negative lower bound estimates, which is a failure. Like if you have a negative lower bound estimates, then that means you didn't sufficiently prove that when this goes to infinity that it's still going to work. So you don't want negative lower bound estimates. So the reason it was negative though is because the amplitudes were just extremely large. So what we did is we discovered that the amplitudes follow Benford's law perfectly. We took 5 million results, and it follows Benford's law to the letter. And so what we are doing is we're applying this formula to the amplitude to dampen it. The amplitude's too large, so we're dampening the amplitude so we can constrain the formula without breaking it. So what we did is we applied the log of the first digit of the amplitude. And I know that's crazy, but Benford's law allows us to do that. And so, as you can see here, it yields realistic, tighter, and generally positive. So then, the next step is to apply the Cauchy stability, which is a known, some other mathematician named Cauchy, if I'm pronouncing his name correctly, he came up with this. So the plan is to use this to prove that the frequencies that I found, now that we've been able to dampen the amplitude, that the lower bound will work until infinity. And then this is addressing the compatibility with Benford, and so together they provide a coherent framework. And if you study Goldbach's conjecture, a lot of people have attempted to prove it, and the lower bound is what always gets them. The upper bound, people I think have been able to prove. It's the lower bound. The lower bound always goes negative because nobody, or because of the unknown predictability of primes, nobody can say for certain that the lower bound matters. So by finding this frequency in the Goldbach numbers system, I don't care what the prime numbers are. If you'll notice, the prime numbers don't matter. We use the prime numbers to come up with the frequency, but now that we have the frequency, it repeats forever. Or at least that's what we have to prove here, right? By using the stability. If we prove that the frequency repeats forever, you don't need to know what the prime numbers are ever to know that the Goldbach conjecture is proven. So the prime index domain and the mod. So here you can see this is when I discovered that we also can form a Hankel matrix, which is what you just saw earlier in this video. So it was actually the Goldbach conjecture research that led to this. So this is getting into the Hankel structure, which I'm not going to repeat. But basically, where I was going is that we might even be able to predict Goldbach using that Hankel thing. But to be quite honest, I'm actually more excited about the frequency that we were able to just dampen with the Benford's law. I think that's simpler and more direct approach to proving the Goldbach conjecture. I honestly think that you can prove it both ways. It's just, I think this way is simpler. So, in here we're talking about how the Hankel thing could be used to prove the Goldbach pair distribution, and I was trying to form a proof. So this one here has been really difficult for me because in order to bound this and prove the bounds, I've been trying to create a data file that goes all the way out to 10 million. So we can capture, because here's the issue with this one. As you can see here, there's a 0 and then there's a 2. So let's look at the number 10. I'm just going to put it here. So 10 would be 7 and 11, which has a delta of 4. So 10 mod 4 would be 2 again, right? So then if we go to the 8, that one would be 7 and 11. 11 minus 7 is 4. Yeah, 8 is 0. So you can see we're starting to form patterns. And this is the frequency stuff I was telling you about. Let's jump to a larger number, 26. Maybe 26 will help us. So the prime below it would be 23. Prime above it would be 27. This is not going to help at all, is it? Well, no, it's going to be a 4. So 26 mod 4, yeah. It's still a 2. Okay, so here's, I promise you, this is what we call the, this is like the frequency domain, right? These numbers go up to 16, and 18 is actually the most dominant. Now, it's not dominant at these low, because these are the lower numbers in the number system. But once you start getting into 10,000 and 100,000, these numbers start to become more prevalent. And 18 is the largest. In the data set that I used, which went up to, it went up to 5 million, I was able to get 18 was the most dominant NMOD delta that we had. And so we call these phases, right? So this is a phase. And so here's what this means. the implications of this. So you got a phase 0, you have a phase 2, and I think there's at least a 12. There's a 16, 18 is our most common one, and I'm not sure it goes much higher. Um, I think there might even have been a 20. Doesn't matter. Doesn't matter what the numbers are. I'm making it up as I go because I'm trying to prove a point. What I'm trying to say though is that we have to show that the lower passes for each one. And when I say lower, I'm talking about the lower bound. I have to prove that as we go to infinity, that each one of these, that this passes, this passes, this passes, that one, and that one. So you need to have all the different of these numbers to be able to do that. And so I'm trying to create a data file that goes up to 10 million. So I would have the numbers 2 all the way to 10 million, so I can capture as many of these numbers as possible. Because the more of these you capture, the better your proof. So the problem I'm running into is it keeps running out of memory and crashing on my computer. I tried Google Colab. I'm having a bear of a time. And in fact, you can see I have all these Goldbach batches that go up to 4,800,000, and then it crashed. So I made it to 4,800,000, and then I tried to have a script that merged all these into one file, and then that crashed. So I'm having a very difficult time just creating a data set so I can test this properly. And the thing is I know mathematicians probably have access to better computing systems, better software that can do this for them, and I just don't have those tools. You can go to ChatGPT and pay some money to. It's like $200 a month or something like that. I mean, I guess I pay more than that on a board game, but still, I'm sort of hitting my limitation on what I, as an amateur nerd, can accomplish with this. So let me just recap, because I know I just presented a lot of information. There are 2 frequencies that I was able to discover using prime numbers. The first one is prime numbers as they relate to Goldbach's even numbers. So Goldbach's conjecture. So using the even numbers that are in Goldbach's conjecture, if you take the prime numbers that are immediately above and below it, it forms a frequency. So all those even numbers form a frequency that you can measure, and you can then, bound it so you can see how it works out to infinity. My issue there is creating the data sets necessary to create that proof. Like the formula is done. The frequencies and those natures of things are done. I need empirical data so I can verify that we did capture all the frequencies and the phases, etc. But that's the part that's missing. But the actual formula for creating the frequency, you can do it at home. Anybody can do it on their computer. That frequency is now, I want the world to be aware that I have a frequency for Goldbach conjecture. And I don't think people have tried heuristic methods and all these tricks to try to prove Goldbach. But I firmly believe that now that we know a frequency, that this thing can be solved in a matter of weeks. With the right mathematician and the right tools. I am neither. But I believe I did the hardest part. I found a frequency. And, well, it's a series of frequencies, but you know what I mean. It's a band of frequencies, but I found it. The Fourier analysis, everything, it's all here. And then the other aspect, the other thing that I found is I created a Henkel matrix using prime numbers themselves. And it has to do with adding 2 prime numbers in the prime number domain. The better way to word it is I'm using prime indices. So if you have a number system where only prime numbers exist, so the number 8, 6, etc., would never be in there, it's basically an index of prime numbers. So if you take an index of prime numbers um, and you try to add them together, and the index that's next after you add them together, because sometimes they don't always equal a prime number, right? Um, you can form a Henkel matrix, and that diagonal of the Henkel matrix is another frequency that's repeatable. And in fact, that frequency is rock solid. The thing that's challenging with that one is you have to adjust for, you have to scale it as you move through the number system. And then you also have to adjust for phase changes. And so if you're trying to create a Henkel diagram, you know, at the number 5,000, if you want to start at the number 5,000 and create a Henkel diagonal, you have to adjust, you have to scale the frequency, and you also have to adjust for phase. So it's going to be different frequency scaling and phase versus if you're creating that Henkel matrix at the number 2 through 100. So, and again, I have my work. I have everything. I actually shared with you some of the most critical elements of the work. I have reached out to 4 professors at the University of Minnesota. I have reached out to professors at the University of Pittsburgh. I have reached out to Veritasium, the YouTuber. I have reached out to an old college buddy of mine. No one's responded. I am being completely snubbed. In fairness to my college buddy, I just reached out to him today, so I actually he deserves at least a week to read his email and get back to me. But the other professors has been a week. Veritasium's been a week, and none of them are responding. And I'm going to be a little transparent here. Some of them have even said, "You're a schmuck." Those weren't the exact words, but that's me paraphrasing, because I'm not a mathematician. Since I'm not a mathematician, it's impossible that I could have possibly done something that they, in all their brilliance, could have done. And that's what I'm running into. I'm running into academia being a little smug. That, the muggles, am I using the Harry Potter term correctly? The muggles don't know magic. So I'm a muggle and I don't know magic. So what I'm doing here is I'm creating this YouTube video to serve as evidence that, look, this is what I came up with. And I have the formulas, and it's repeatable. I can do it. When we get into this here, I'm predicting prime numbers, dude. I don't know what I don't know what to say. This, I'm empirically showing it can be done. I have my script. I'm willing to share my script. It's all. There's no magic here. There's no smoke and mirrors. The only unknown elements is that I'm struggling to master these tools in a field that I am not. They're right. I am not a mathematician. So I can do some pretty, what I believe to be impressive things. And I don't believe mathematicians have been able to do what I just did. But that's the reason why I want a mathematician's help. Because, if there is something flawed in my logic, I want them to help me to see it. And then the other part of it is I don't want this to die. Because I don't know how to take this to the next level. I don't know how to get something like this published. I don't know how to help mathematicians. I believe Goldbach's conjecture is solvable with these frequencies. I believe that this can help us to find the next prime easier than asking 3 million people to install some background running process on their computer while they sleep. So I just want help because it's here's my analogy. If I just discovered something that could lead to the cure of cancer, but I'm not a, a biologist able to run the experiments to prove it, I mean, it dies with me. So, I'm trying to get somebody who has a proper lab and the proper skill set to confirm what I'm doing and then take it. Take it to where it needs to go. Because I want people to be cured of cancer. I'm sticking with the analogy here, right? I want this. I want society to benefit from what I discovered. I discovered frequencies in the prime domain, and I Google this stuff. I can't find anybody who's ever done this before. I've been told that prime numbers are unpredictable. There is no pattern to prime numbers. Well, right here. I was able to predict them. 100% accuracy. Every single one of these is correct. There was not one error in this prediction. So that's what I'm trying to stress. I found a pattern. I found two patterns, in fact. One of them, of course, is specific to Goldbach's conjecture, but this one is specific only to prime numbers. Anyways, I think you get the gist, and that's it. This video serves as, first of all, in case I get hit by a bus, this serves as, proof that I did this. And also it serves as proof that I did this in case some jerk tries to steal the idea and claim it as their own. And then lastly, this is a plea for help. I'm just looking for a mathematician that can sit down and help me to formalize this and prove this using the right tools, the right techniques, the right procedure. And, and if it turns out to be nothing but fool's gold, I apologize for wasting someone's time. I just don't believe I am. I believe that these frequencies I found are legit. Now, whether or not those frequencies can be used to, cure world hunger, I don't know. That's the part where I need the help. So I don't think it's going to be 100% fool's gold. I think I found something that is going to be useful. And who knows? Maybe the fact that I found this frequency, once other mathematicians learn how I discovered these frequencies, they might discover more frequencies using similar techniques that I haven't found. I mean, that's the way discoveries work. Is somebody didn't just cure penicillin right away. They realized, over time with experimentation that, hey, this works. So, anyways, that's all I'm trying to do. I am frustrated, and I understand and I completely respect that mathematicians are probably bombarded with muggles like me, and they don't want to waste. They feel like it's a waste of their time to even pause and look at these ideas. I get it, because if somebody who doesn't work in my field that I do from my profession, it's a bit of a Dunning-Kruger kind of effect, right? When somebody starts talking to you and they, and you immediately are like, and so how many years experience do you have in this industry? 0. And now you're telling me that you've discovered something that my colleagues who are, been doing this for a lifetime never discovered. I mean, that's a hard pill to swallow. And my answer is yes. Yes, I did. I discovered something. And I just want to know how valuable that something is. Is it just a parlor trick that's going to be, on the next Veritasium video? Which, by the way, Mr. Veritasium, whoever you are, because you snubbed me, You don't get to claim any credit for anything, and I am certainly not putting any of my stuff on your show. And you don't have the rights to put any of my stuff on your show, you jerk. But obviously, a very nice apology from you will change my attitude about you, but right now my attitude about you is not good. Anyways, that's all. I just, I discovered something. It, what's it worth? I need help identifying its value. So, anyways, thanks for watching, everybody. Stay awesome.